We can start maybe. Hi, good morning, everyone. So my name is Tolias, and I will be giving the 3 last lectures in this course after all Sasa's lecture. So it will be today on graph neural networks, then following with attention and transformer networks, and the last one that will be less technical. Hmm.
Diversify the teaching a little bit. We have many experts in many different fields. So Georgos is an expert in self-supervised learning topics. Then I assume it would be a benefit to the course if many teachers would teach different topics.
Okay. For sure, I have done some work with graphs and graph neural networks. I cannot easily indicate to be an expert in this field that is, very thoroughly studied in graph theory, graph signal processing, and today we're giving one lecture about graph neural networks, which is also well studied, and there is like very rich literature the last 10 years in this field. So we're really scratching the surface of what graph neural networks are and can do, and we'll talk about the basics today. Yeah. Okay. So why to bother about graphs, right? So briefly to say, because real world data are often relational, okay? So data points, the data examples do not just exist by themselves, but there are established relations and interactions between them. And for some tasks, it is really important to not focus on processing isolated points in the way that someone does with a multi-layer perceptron. You have an input vector, you have an output vector, you process the vector separately and independently. So there are interactions and connections that are inherent in the data and really relevant to some tasks. So because the graphs can provide a network for a framework for representing the entities themselves, but also the relationships among them, and all that forms some very structured information that is not available in other data structures, like if you're dealing with lists or if you're dealing with a 2D grid. That is also what you have seen and worked with in processing images with convolutional neural networks, where indeed we process many pixels together, and there is relationships between pixels, but they lie on a uniform 2D grid. So that's much less powerful in terms of the different structures that it can represent. And by using graph, we inject some inductive bias about some relational inductive bias in the processing. That's some kind of built-in assumption that in a model that the relationships between entities really matter, and they should be taken into account. This should be a fundamental part of the learning process. And moreover, there is different kind of information. Within a graph, we have nodes, we have edges, we have holistic representation about the graph, but also about the nodes and the edges. So there is like rich information at multiple different levels that one should be able to exploit during the learning. Just to go through a bit some application domains and briefly mention some relevant tasks. For sure, we're dealing with graphs in science and biology. One example here is molecular graphs, where you have atoms that are forming the nodes of the graph, and we have chemical bonds between the atoms. So these are the edges of the graph. And there often we might have to deal with making predictions for a whole graph, for a whole molecular graph, to predict some properties. for instance, or to perform drug discovery and so on and so on. You know, in the same field, there's also protein interaction networks where you have proteins and edges between them because of their interactions, and we're supposed to predict properties, predict functions of the proteins. Another very popular domain, you know, social networks. They're all over. You know, we want it or not, we're part of several of them. And there you have users that, you know, nodes are represented by the nodes, and then you have, like, you know, friend relationships, follower relationships that are now the edges between the different users, and someone, you know, might want to do user profiling or make some recommendations and so on. Here another case is recommendation systems. Here actually we see the flexibility and the power of graphs, that we can also model heterogeneous information. Like we have an heterogeneous graph where not all nodes are of the same kind. You have users, you have movies, you have directors that are, you know, different kinds of people with a different role, and relations among them. Maybe a last mention is transportation networks, where actually there was supposed to be a breakthrough a few years ago, around 2021, where in Google Maps, you know, the technology behind it was switched from handcrafted, you know, engineered algorithms to graph neural networks, and this was supposed to be, you know, a big boost in terms of performance in predicting traffic, optimizing the routes and so on. Okay, so that's another very relevant domain. Right, I'm good catch, because I don't know all the details about it, right? Okay, I've seen it, you know, mentioned it, but I don't know all the details. If you ask me, you know, what exactly was it, yeah, that's why I used that, but there was, okay. Yeah, and actually, yeah, I'm also not sure exactly, you know, to what amount, you know, of details are out there, you know, are all details in a publication that is, you know, publicly available about what, but yeah, this has been information also in the news, but that's why I used suppose, which maybe anyways was not the correct one. Okay, and now, you know, what are the graph functions that we will try to learn? What are the relevant tasks that we will work on? So we talked about, you know, we have nodes, we have edges, and the whole graph, and actually we will be dealing with predictions at all these different elements, right? Node level predictions. So for instance, like typical classification tasks where you're supposed to predict the type of a node, okay? Or regression, predicting like a real value property of the node. Well, I'm also listing here representation learning. Okay, in some sense, sometimes this can be like kind of, you know, multi-dimensional regression. Similar edge level predictions. Maybe a very common task is actually link prediction. You're supposed to predict whether there should be an edge there added or not. So that's binary classification at the level of edges. Otherwise, of course, multi-class classification makes sense as well there, because for different kinds of graphs, as the ones we talked about, you have, you know, interactions. We have interactions between proteins or bonds between atoms, and you have different types of relationships to predict. Regression, representation learning as well, and then lastly, you have also graph level predictions, where now you treat the whole graph, okay, despite the fact that it is composed of many different nodes and interactions among them. You're looking at a single prediction of at a graph level, and you will be making predictions for many different graphs. Okay, also some different cases that I'm not listing here, that you might be making, you know, some predictions about like subgraphs, or maybe grouping nodes into subgraphs, but somehow maybe this can be mapped here, that you're learning representation so that you can do some sort of clustering. Here is an example that actually illustrates all these different kinds of predictions, that you have like a graph that is reflecting an e-commerce scenario. You have users, you have buyers, and you have an e-shop, and the users are purchasing products, right? And that's why you have like here interactions between users and products. So products, these are the edges of the graph. So a node level prediction for, let's say, the customers is the churn rate. So this is like the rate of them just not returning and never purchasing anything new. At the edge level is like, okay, the edges now are, we said, interactions between users and products. So it's like recommendation. This is, this user is likely to like this product, so let me make a recommendation here. So that's an edge level prediction. Or a graph level prediction is actually, that's an interesting case, is that you have a whole graph like that, and you're trying to predict whether this is some money laundry business. You have different graphs that represent different, correspond to different online stores, and you can have training data for that, trying to predict money laundering. Just some basic simple notation, which might be changing like over different slides, but just to touch base to start with, we have a graph. It's a vertex set, the node set, and an adjacency or affinity matrix A. So if, let's say, here we have n equals the number of nodes, A is an n by n matrix, okay? So we refer to it as adjacency, which is not always but typically binary. It indicates which are the linked nodes, which, let's say, are all the neighbors of a node. Well, in the case of an affinity matrix, we have typically real valued matrix, where we have the affinity, the similarity between two nodes that may, for instance, like vary in a bounded range between 0 and 1. Then the feature matrix X, which is essentially like the features of all nodes concatenated together into a matrix. So this is what we should see as a graph signal. It's a signal over a graph. So you have like one high dimensional vector per node. Okay. So you have a signal that varies across the different nodes of the graph. And here by this, n of I, we will be often indicating the neighboring nodes of node I, which is, this is meaningful when we have a sparse adjacency or affinity matrix. The affinity matrix can sometimes in some tasks also be a full matrix, right? That there's no zeros at all. So in this case, this n, the neighboring nodes, doesn't make any sense because everything is, neighboring with everything. It's just that there is a different affinity value they're indicating. Okay. And in a very simple case, the graph neural network will be a function f that is not only a function of the features, but is also a function of the affinity matrix. And here this y, we can see, depending on the different tasks and graph functions that we talked about before, you can see it could be a representation for the whole graph, or it could be different representation for the different nodes. So this could be a single vector, a whole matrix, and so on. So something important to keep in mind is that the graph does not have a canonical ordering of each nodes, right? So even if we're listing the nodes in a particular order, let's say we're listing them because of the ordering of the vectors in this feature matrix or in the affinity matrix, this is a bit arbitrary how we decided to order the nodes. We reorder them, if there's, and the topological structure of the graph does not change. It's exactly the same graph. So many different orderings actually represent exactly the same graph. And this is what we refer to as isomorphic. This keeps happening, or it will come back? Okay. Good. I didn't do it. What was I saying? Yeah, many different orderings of exactly the same graph, yeah, and all these different representations are actually what we call isomorphic graphs, right? They have exactly the same structure. They're the same thing. Yeah, and we might be dealing with directed or undirected graph, homogeneous or heterogeneous. We talked about heterogeneous, where you have different kinds of nodes that are interacting with each other. Now, it is good to differentiate between different origins of adjacency or affinity matrices, right? In some of the tasks that we talked about, it was already part of the data, right? We talked about social networks, and then we have the following relations. And these follower relations give us the adjacency matrix, right? It's part of the input data, or the same with the molecular graphs. These are the bonds between the atoms. While graph neural networks and graphs in general are also applicable in other tasks where there is no such information as part of the data, but we derive it. And commonly, how we derive it is from the features. So we have nodes and node features, okay? And the common way to derive an affinity matrix is by a KNN graph, okay? So this is the case in a point cloud, okay? We have a point cloud, a 3D point cloud that represents an object. And then what someone can do is you take this and you find the nearest neighbors in this 3D dimensional space. And based on these neighbors and actually a function of the distance, we create an affinity matrix that is now sparse. So now this affinity indicates the relationship between the data points according to the distance in some feature space. The feature space here is a 3D-dimensional space. We have a 3D point cloud. Okay? And actually this is useful to capture the structure and the shape of such an object in ways that just like, you know, the mere set of 3D points concatenated into a feature matrix cannot necessarily indicate. So it's some sort again of inductive bias that we inject to the model. Or other cases that actually we have, you know, really worked on something like that, that you may do the same with the representation of images in a high dimensional space. That one image is mapped to a high dimensional vector, yeah, and now we want to capture relationships between a large set of images, and we do this by a KNN graph and the corresponding affinity. And this is again useful to capture some, you know, structure that looks like that, like nonlinear manifolds in the representation space. And of course, in such cases, it is also common that the affinity matrix might be changing also during, you know, the processing time within a graph neural networks. Okay, graph neural network, because we did that with some originally given features, but the features of the nodes are changing during the processing, and the affinity might also get updated. Okay. So now let's talk a bit about let's say the training and testing examples that we're dealing with when working with graph neural networks, mainly to talk about two different learning schemes. The first, what is called transductive learning. In transductive learning, we're dealing with a single graph, but during training, validation, and testing. Okay, not talking about validation, but you see the relation. So we have a single graph, and some nodes, okay, equivalently edges, but let's talk about nodes. Some nodes have labels, and these are the training examples. All other nodes do not have labels, and these are the test examples. So all we're interested in is in making predictions for these unlabeled for the unlabeled nodes of this particular graph. So it's really a closed world. We're not interested in making predictions outside of this closed world, which is a more general problem, might be harder. So this is what is referred to as transductive learning. Often this is equivalent to semi-supervised learning. You can see as here we have labels for some nodes. Let's predict for all other nodes. Okay. And in this case, graph level predictions are not meaningful. We're working on a single graph, right? So we only focus on node or edge level predictions. And then in contrast to that, we have inductive learning, which is maybe what you're more commonly used with the lectures of this course or machine learning in general, where you have a set of training data and a non-overlapping set of test data, right? So you could have a set of training graphs and an overlapping set of testing graphs. Yeah? So no matter whether we are making predictions at graph level, learn on the training graphs, test on some unseen graphs, yeah, or on nodes of these graphs. And the goal here is to, of course, generalize to graphs that have not been included in the training. So now let's talk about some very essential property in graph neural networks, which is permutation invariance and equivariance. And maybe before that, let's recall that in general for a function f with input x, yeah, we call this invariant to a transformation t of the input if the transformation doesn't play any role, okay? Or we could also apply here multiple different transformations, t1, t2, so the result is always the same. So this is invariant, while in the case of equivariance, what happens is that we have not the same transformation, yeah, but a corresponding transformation that is applied on the output. Okay, that's the general case. So now let's focus on permutation in terms of nodes. Okay, we're permuting the yeah. Well, not necessarily. It all depends on the design of the functions. For instance, like the most common example to mention here is convolutional neural networks, right? That you have a CNN, yeah, and at the end of the CNN you have global average pooling. So the output of the whole network with global average pooling is invariant to translations of the objects. Yeah, no matter where the object is, the output is invariant. But if we forget about the global average pooling and we focus now on the 3D tensor representations, that's equivariant because we translate the object, yeah, and the relevant activations are also getting translated, but in a different way because the resolution is different. Let's say, yeah. So this is why this is T prime, yeah, and it's not exactly T. If you would design a convolutional neural network without any stride or 2x2 max pooling, then you would be getting exactly T. Yeah. Like, translation by 10 pixels would correspond to translation by 10 pixels. Yeah. Yeah. Well, not exactly, yeah.
Well, the question was like, does there need to be a deterministic transformation that we can do on T to get T prime, like, so that we can derive T prime from T, but I guess that's not necessarily.
It's
I think it is a generalization that comes from this group theory stuff, because they introduce only definition like that, so there is like action of this transformation on the representation before the function and an action of this transformation on the representation after the function. For example, you take the data from the sphere to some other space, and there the transformation T needs to be defined also somehow. And they go even like further than they would say, okay, if you say T prime to identity, that gives you invariance. So they say invariance is a special case of equivariance, which makes things like fully confusing.
Yeah.
So we can distinguish invariance, and the equivariance
That.
would be just in this case, it would be the same.
So now we'll focus on permutations of the node ordering, right? And that's what is done with a permutation matrix. So this permutation matrix is n times n if we have n nodes. And maybe good to give an example here that there is only no, that's 0. One, let's say we have 3 nodes, there is only one non-zero element per row and per column. So this would be P, we transpose it and then we multiply here with X. That X has the features of a node as columns, right? And the result here would be that actually we're swapping nodes 1 and 2. Okay? The first row says that actually I'm picking node 2. The second row says that I'm picking as second node, I'm picking node 1. So here we multiply from the right, we're permuting the columns. Okay? So here what happens with the affinity matrix that we need to permute both the rows and the columns. To do that, so we multiply with from both sides. Is this all good? Okay. And now permutation invariance. We require permutation invariance at the graph level for graph level predictions. So this would be, we indicated we wrote the graph neural network before as a function of the affinity and of the feature matrix, and at the very output we have a representation for the whole graph. And that's what we want to be invariant. You change the order and the graph should be represented in the same way because it's exactly the same graph. Yeah? So this implies that in the same way that we wrote the invariance there with transformation T, we're applying the permutation as a transformation on both inputs, and the result should not change no matter what the permutation is. So maybe a simple example, one could say that if I ignore here A and say I multiply here with a vector of ones, which means that I sum all the vectors. Yeah, this is sum pooling of all the node vectors. This is invariant. No matter what the ordering is, sum pooling is invariant to this order. And then permutation equivariance is desired to have at the node level. So this is kind of similar to the example with the CNNs. Okay, the object was translated, yeah, and we want another position of the activation tensor to have the same activations. Now we want another node to have the same activations because we reordered them. So in this case, we change the order of the nodes and the output should change accordingly. And the output here is a matrix where we have a d-dimensional vector per node. And the order of the columns now should change according to the permutation. Okay? Similar, we might want to do that at the edge level. Okay, so that's correct because the model should respect these graph symmetries, right? These graph equivalencies, and it's also good for generalization because you will see then exactly the same graph in different orderings. If this wouldn't be the case, and there would be some kind of dependence in the ordering on some kind of order encoding, then you can imagine how it would be a more data-hungry model to try to see all different orderings so that you can tell that these are actually the same thing. So in this way, we generalize in a data-efficient way because all these things are equivalent the way they should be. Okay. All good so far? So, how are the few following slides are going to go? I'm picking a very specific task, yeah? Semi-supervised transductive learning for node classification. Yeah? Somehow we discussed about it. And first I will discuss a classical approach, a graph-based approach, not a deep network, okay? A classical. so that somehow this will help to understand the evolution of graph-based learning methods and see how the core ideas are transferred to deep learning and graph neural networks. So what is the task? We have a single set of data points, okay? And some are labeled with categorical labels, all the others are unlabeled, okay? And the goal, as we said before, is to infer the labels of the unlabeled examples. We will work a bit on this toy example, okay? These are 2D points. The colored ones are labeled in 3 classes, all the other ones are unlabeled, okay? Here we're given a feature matrix, yeah? Actually, the features here are the 2D positions, and we have a label matrix that is one-hot encoding when a data point is labeled. Otherwise, the corresponding column of this guy here is full of zeros. Okay, so the goal is to transfer labels from those 9 points to all other points. And this is, let's say, a classical label propagation algorithm. There is many different variants in the literature. I'm picking, one that is somehow principled. We'll see later why this is, a more principled algorithm. So the first step is to construct the affinity matrix, and we construct this from the features. Okay, so in the very general case, it could be just dot product cosine similarity between the features. In the toy example that we saw before, it's actually we're using an RBF kernel, so the affinity is a function of the distance. Yeah, RBF kernel. So this is the Euclidean distance between the 2 points, and there is some sigma here. So the closer they are, the higher the affinity between the two. And again, it's a KNN affinity, so only the k nearest neighbors have non-zero values. All the other ones have 0 values in the affinity. So, this is an example, but the toy example is created in a bit different way. And what we need is the normalized affinity matrix, which is, as we call, symmetrically normalized. So this corresponds that every element here is actually divided by the square root of dii times djj. Yeah, and dii is the summation of all the affinity values for a corresponding row. This is the so-called degree of the matrix. Yeah, it's the sum. If it's the sum of a row. Yes, the sum of the edge weights for a particular node. So we divide by the square root of the product for the 2 nodes that are getting linked here. Actually, you also have, like, very commonly this version used that gives you a stochastic matrix, so that the rows are normalized to sum to 1. But in practice, the symmetrically normalized has also different properties and works better in practice, so it is a bit more established in many different algorithms. But otherwise, you could also do the similar work with S like that. Okay, so S is a modified affinity. Yeah, there's some normalization. And what happens in label propagation is this iterative scheme that does 2 things. Okay, and there is a balance between 2 terms. Here there is the propagation term and the term that actually respects what the initial labels indicate. So now we focus on a class, on a specific class. Can I go back here? Yeah. Let's say you focus on the red class, yeah, and you have a vector that has as many dimensions as the data points and has 3 non-zero elements. Okay, 3 values of this vector indicate 1, that these are labeled. These have the maximum confidence for this class. And here, the current vector is actually propagated through the neighbors. Yeah, we have a signal here, y, that we keep updating. And we say that for the first node, I'll find the neighbors, yeah, this neighbor, this neighbor, this neighbor. Actually, I'm doing a weighted summation of the values from the vector y here. So whatever the vector y here will be accumulated now to the first node. So in this way, you know, the red now points will propagate their label to their neighbors, and then their neighbors to their neighbors, and so on, because we run this iteration many times, and there is a balance alpha. Maybe if this is interesting to you, actually alpha typically is, you know, between 0 and 1 with very high values in the range of 0.9 something. All good? Okay. So let's see how this works in practice. Yeah. So now we focus on one class and one data point, okay, to show this example. And then we start iterating, and the size of the circle is actually the current confidence. Means maybe if I go back here, I can say that this vector is n times 1. This also is n times 1. Yeah. So here we have like the one hot confidence as indicated by the ground truth labels, and here is like the confidence after propagation, and this is what is visualized here with the size of those circles. We iterate and we see how this confidence gets propagated over this nonlinear manifold. Okay, so because of the structure that the affinity matrix indicates, we're propagating in a very different way than what Euclidean distance would indicate. Yeah, so here is like this on the left, the circle size is inverse proportional to the Euclidean distance, and we see how you drift into a different nonlinear manifold, while here you crawl the manifold, yeah, through this propagation scheme. So this is what the affinity matrix provides by capturing the structure of the feature space and through the relationships of the data points. Now, how do we do this for classification? Yeah, we have the three classes. We run this for the three different classes, so we get the confidence scores for all the classes, and then we do argmax and we label the other points. Yeah, iterate, and that's the result of, you know, classification through this label propagation algorithm. So we worked with this iterative approach, yeah, here. However, one can show we didn't talk about how to initialize. You know, what is this y at iteration 0? We never talked about it. Interestingly, it really, you know, it doesn't matter as long as you iterate until convergence, because there is a corresponding closed form solution. And this takes into account this matrix here, L, that is again a function of the affinity. Yeah. This actually is very related to the graph Laplacian, which we're going to see later. But at the end of the day, we see that, okay, there is a closed form solution, but there is an inverse matrix here. S was very sparse, and actually when we do the matrix to vector multiplications during the iterations, that's very efficient to do. But now if we have like to compute the inverse of such a very large matrix because of very large graph, that's not necessarily very convenient. Anyways, so now the most interesting part is that all that is actually the minimizer of such a quadratic cost function. Okay? So it has two terms. Here we can call this a supervised term. So here this is what tries to respect the label. So the output labels, this is the label vector, okay, over the different classes for node I. Should stay close to the original labels. And there is another term that is the pairwise term that focuses only, it's the unsupervised term that focuses only on the output predictions. It says that the output predictions between two nodes I and J, yeah, should be close if Aij is very high. If it's 0 or very low, we don't care that much. But when this is high, these two things, okay, there is also some normalization here with respect to the matrix degree, should stay close. And that's hopefully, you know, much more intuitive. It's what we call smoothness assumption, that, you know, nearby inputs, yeah, as indicated by the affinity, should have nearby outputs. Maybe something to note here, that in these, you know, classical approaches, we got rid of the features. We just created the affinity matrix, and now this affinity matrix, which is a graph, actually lets us propagate a signal over the neighbors. And the signal was the originally provided labels. But the features, they didn't play any other role afterwards. And now we're switching to graph neural networks. Okay. So, in contrast to the previous cost function, yeah, maybe one would expect, okay, we see where this is going. We will have a similar loss, you know, like the pairwise loss in the graph neural networks. But that's really not the case, because that's also not easily scalable, you know, to include the loss between pairwise terms. So there's no graph-based regularization in the loss. Okay, so what we do is that we encode the graph structure via this network that takes the affinity matrix into account. And such a network is a sequence of such processing blocks, such layers. So here, that's again a hat, because it is a function, okay, a bit different function of, again, the affinity matrix. And H is the latent representation of nodes. Okay, at level 0, these are the input features. So now, if it was understood before how this matrix, you know, to matrix here, yeah, matrix to vector before multiplication does propagation over the graph and over the nodes. So this does a similar process, but now the signal are the features of the nodes. Maybe if it helps to talk a bit about the dimensionality. Not enough space, so A is n times n, yeah. Then we have the features. Okay, here transpose from what I was writing before, right? Yeah, so now we have like a row features instead of column features. Yeah, that does the propagation. And what are where are the learnable parameters? They're exactly here. So, and this is a D by D matrix. So this transforms the feature space. So it does two things, like propagation through the neighbors and transformation of the feature space, plus a nonlinearity. So you could see this as, you know, two things. You transform the original features and then propagate, but operations are linear, so it's equivalent to you propagate and then transform. Okay, and these are the trainable parameters. And this is what we refer to as, you know, graph convolution over graph. So in the 2D grid and with convolutional neural networks in images, you take into account a local neighborhood, again the neighbors of a pixel, to get the updated representation of a pixel. So here we take into account the neighbors, as these are indicated by the affinity, to have an updated representation of the node. Okay, so maybe this is not the most important to follow on the fly right now, but, you know, again, there is symmetric normalization of the adjacency, and there is some adding of self-connections, assuming that they were not part in the original adjacency. So now that we know the main building block of such a graph neural network proposed by Keefe and Wellin in ICLEAR 17, yeah, we can go back to the tasks to the specific task that I said I were studying, for a bit. So this transductive semi-supervised node classification. And the authors of this paper deal with this simply with a two-layer GNN. Okay, two layers means we have two hops on the graph. Okay, we go to the direct neighbors and then to the neighbors of the neighbors. This is what happens here. So one layer is that, okay, said W0, the learnable parameters of the first layer plus nonlinearity. Then this goes in a second layer that has a softmax in the end. So here the dimensions of this matrix should be so that the output is has as many dimensions as the task requires. 3 dimensions for the toy task that we were talking about before. Okay. Yeah. Yes, so the output here is n times c. This, because we said this, should be, if we're staying, if this is d times d, then this is d times c, so it maps to, 3 logits in the toy example. And now the softmax is per node, yeah. It's independently per node. So it is applied in this matrix per row. Softmax per row. And then cross-entropy loss. Where do I apply cross-entropy loss? Only on the nodes for which we have labels. There's nothing else. We do nothing about all the other nodes during the training. Okay. But what happens here is that, in this way, because of the affinity matrix taken into account and the propagation, there is distributed gradient information from the supervised loss to all the other nodes. Somehow, the forward pass does mixing of the features. And then during the backward pass, we backpropagate gradients to all the nodes because of this mixing. During inference, what you need to do is just take the predictions here for all the other nodes. You already have them. You process all the nodes at the same time. You iterate, you update, okay, you do, there's no mini batch sampling here. Like, you process all the nodes of the graph jointly, and at every iteration, you apply the loss, you backpropagate, you update W0 and W1. Yeah, yeah.
So from the task definition, we have the target labels on some of the nodes. And we predicted them, but we also predicted all labels for all of the nodes.
Yes.
And what the training does is that it wants to train such that we are predicting on the level of nodes correctly.
Yes. Good point, because good point, because this adjacency, it's not learnable, it's not completely free. If it would be learnable, maybe that would be such a shortcut. But there is the inductive bias of the structure, indicated by the graph. So the graph indicates that there is a relation here. A relation means this should have similar predictions. And they tend to have similar predictions because of the mixing of the representation through this operation. So yeah, going back here, this is labeled, this is nearby, yeah. So they're kind of end up having like, more similar representations, and then we apply a classifier on those representations.
The features and the next step for each node are a weighted sum of the features of its neighbor weighted by
And that's maybe a difference between the classical approach and this one, that the features here did, you know, play all this role. We mix the features and then we apply the appropriate head. Here is a classification head.
So it has a similar structure of averaging the features from the neighboring nodes.
Yes. So
But then it's only like 2 steps of that. So the previous algorithm that you presented, the label propagation was iterate, and then it propagate far along.
good point, and it converges to good point, and it converges to something meaningful, right? And this is only 2 steps, and now you know what is the extent of the affinity. We're going to touch that in a bit. Yeah, indeed, actually, you know, in this seminal work, it was a 2-layer network, and 2-layer networks have been around, you know, for a long time. But we're going to come back to that in a bit, okay? Now, something that is interesting is that relation to MLP, yeah, to multi-layer perceptron. So if you set the affinity here into identity, it's equivalent. So now there's no mixing anymore. You process each one independently. Yeah? Okay. Give me a second. I think I'm doing bad time management to see, but what follows. Okay. We'll see how that goes. So now maybe what is a bit interesting is to see a relation between this graph convolutional operation, yeah, that happens, let's say, we could say in the time, the spatial domain, yeah, by going over the nodes, and the equivalence between spectral convolution in the frequency domain. The same correspondence that exists also for, you know, 1D and 2D convolutions on a uniform grid. And this is what is given by the same paper by Kiff and Welling. So we have the standard equivalence that, you know, the convolution should be equivalent to multiplication in the frequency domain. And what is the frequency domain in the case of a graph? Yeah. So in the case of a graph, we have like the graph Laplacian that we're not going through, you know, that so much, you know, today, but this is given by this matrix, the symmetrically normalized graph Laplacian. So our favorite affinity matrix is here, yeah. And the eigendecomposition of such a matrix actually gives us the Fourier transform. The eigenvectors here, given by U, take the graph signal, x now we can see it as a one-dimensional signal, yeah, a scalar per node, okay. It takes this and it transforms it does the graph Fourier transform, okay. So now we're in the frequency domain. If we multiply by U, we go back. Okay. Actually, the filter function here is a function of the eigenvalues. Okay, the eigenvalues indicate the frequencies that are present in the graph. Yeah. So this might be not easy to digest, yeah, at this stage. So it could be a bit, you know, hand wavy so far, but let's see that. That's here we have a signal, we have a graph, and we have a signal. Okay, the colors are the one-dimensional signal on the graph. And what happens here is that we transform it to the frequency domain, and we apply a low-pass filter. It's a filter of the eigenvalues. We manipulate the eigenvalues, yeah, of the graph Laplacian to do graph signal processing in the frequency domain. And the low-pass filter would be something like that, you know, it lets the small eigenvalue survive. Yeah, this would be lambda eigenvalue, and not the large ones. And we see the result that indeed, like, you know, rapid changes among neighbors are filtered out and smoothed out in the result. Yeah. Hmm.
If we do not change the graph, why would the eigenvalues of the Laplacian change?
Because they reflect changes among neighbors. That's in the same way that, you see frequencies in the 2D image, right? You see frequencies as changes, you know, the amount of change among neighboring pixels. The same way among neighboring nodes, how much a signal changes. So if
The Laplacian is given by the graph on the affinity matrix.
mm-hmm.
That's fixed, and this the basis.
Yeah, this forms the basis. Yeah.
Eigenvalues are somehow also fixed. But when we multiply in the frequency domain, then the signal frequency gets multiplied, right? It changes.
Yes.
But not the eigenvalues of the graph Laplacian. That stays the same.
Can you say again? What you okay? So what we do if here if we manipulate the frequency exactly? So yes, it will suppress, you know, yeah, the relation to some. They stay the same. That's true. They stay the same. You could see it as a fixed function, or you could see it also as a function of the eigenvalues, if it helps. And somehow you might be learning one or the other. So the filter here, now that you're learning, yeah, does exactly that. Like, can learn how to manipulate frequencies of the specific graph. Okay. Well, okay. I get it. That's why I said at the beginning it will not be easy to, you know, digest this on the fly. Yeah. But let's, you know, take for now that this is the graph Fourier transform, okay? And there is a correspondence there. And now something else that, of course, we're not going to follow the math. Here, the authors of this paper say that with the use of Chebyshev polynomials and some properties of you know, the eigen decomposition, they have an approximation of such an operation, yeah, that at the end of the day looks like that. And these are here simple scalar parameters that are learnable. And if you do one more thing that you said, okay, maybe I can reduce the number of parameters, so tight connect, you know, relate theta 0 and theta 1, then now this starts to look exactly like the operation that indeed we're doing in the graph convolutional networks. So they're saying the operation, the layers that we presented before are actually an approximation of the spectral convolution that operates in the frequency domain. And we can move on. Okay. Now a bit of a relation between the graph convolutional operation and the 2D convolutional operation. Okay. See, of course, it's a very different, you know, domain. We have, let's say, one central element or node, yeah, and the whole 3x3 neighborhood in the 2D image, yeah, or these 9, including itself, neighboring nodes in the graph. So we have 9 input vectors at the input. In the 2D convolutional, these are stuck, yeah, as a 3x3 by D matrix, and this is what we process with a 2D convolution. And what we care is about, okay, what is the output representation of the central pixel? So, and actually we can rewrite the 2D convolution, which would be the multiplication between such a matrix, the parameter matrix, and the input. But we can rewrite it as a summation going over these 9 vectors. And now we have here a product between this matrix and the input vector. So this goes through the 9 input pixels. Yeah? And this matrices here are, these 9 D by D matrices. So essentially here also we're doing a summation across those 9 neighbors. Okay? And we're doing a different projection of each of the neighbor with a different matrix. Now if we go back to the graph convolution, the graph convolution, before we saw it in a, we did things jointly for all nodes, so it was an affinity matrix multiplying all the features of all nodes. But this is equivalent again to a summation over the nodes, and the representation of a neighboring node is multiplied by W. W is, oops. W is this W, yeah? The single learnable parameter of the graph convolution. We multiply it by that. The difference now is that it's exactly the same W for all the neighbors. So this has a bit more, limited expressive power compared to the 2D convolution, that based on where the 9 neighbors are, you will be projecting them in a different way. So it matters differently if I'm above or below. Here it does not. Nevertheless, there is a different adjustment, which is the scalar here that comes from the affinity matrix. That is a different kinds of input, given maybe from the input data or like from the relation, the similarity between those two. Yeah.
So can you summarize the message here? So if you consider convolutional graph neural networks defined in this or the other way of the two that you presented, and compare it with the plain convolution in the case when the graph is actually chain or every.
Okay.
Yeah.
Right. So this would be, as I said, it's less powerful, the graph convolution than the 2D. Yeah. It would not be possible to differentiate between what is above, what is below, right? This spatial relationship would not be taken into account. So it is less powerful, it is less appropriate. Nevertheless, the 2D grid is not as flexible, to represent different kinds of data as the graph. So that was the message. No, here it's the exact. The approximation was only to make the relation between the time domain and the frequency domain, the spatial domain. Right. That was only the approximation was only there, and then we forget about the approximation. Yeah. So other than that, hopefully, the propagation operation should be, clear and intuitive about what happens within a graph convolution. Okay, so here some years ago, some people presented a more generalized framework in terms of message passing, which encompasses, or at least back then encompassed, many different graph neural network variants. Okay, and this reduces down to establishing messages from a node J that is a neighbor of node I. Okay, and here what is this? This is done by a differentiable function, which is like a neural network itself, that takes into account, in the general case, the latent representation of the node of interest, the latent representation of the neighbor, plus any representation for the edge. Then the next step is that we aggregate now the messages from all the neighbors. To get the input message for node I, we collect the messages from all the neighbors, and we do some aggregation operation, mean, sum, max pooling. Okay, so the output of this function here is a high dimensional vector, right? And now we're aggregating these high dimensional vectors to get the message. And then there is a node feature update, which actually says I will take the message and I will see how to combine it with my current representation of the node. Doing this multiple times, you know, t index is how many times we do that. And maybe now I'm afraid to touch it. You think it's okay? So for instance, you can see here that if you have the output of MT to be Cij 8jt. Now, okay, we're trying to see how the one of Kipfen-Welling, the one that we said before, fits here. But Cij is actually the affinity between ij, yeah, normalized, as we were doing the symmetrical normalized matrix. And then the update function, okay, I'm skipping here the whole notation, just was actually RLU maybe it helps to say here that this is actually mi from j. So the message from a neighbor is like, okay, I transfer my representation to you multiplied by this weight. Okay, the aggregation is missing here, but the aggregation would be mi summation. Yeah, now we're going back to this MT. No, that was correct. T plus 1. Yeah, I get all the messages and I aggregate them. And this gives us what Kipfen-Welling have done. Or maybe some other cases that are a bit interesting to see how different kind of information is used is to say that here there is a learnable matrix. So here is the message coming from node J to node I. Yeah? And this is the representation of node J, but is multiplied with a different matrix. So this is a discrete label. Here, this is for a setting where edges carry discrete labels. Okay, there's a discrete set of different kinds of edges, and for each one I have a different learnable matrix. So for a different edge, I transform the message in a different way. Or tac. Oh, pop. Or here the update functions that you have. We said the updated function is how to combine the message with the current representation. Here, that was I. In Kipfen-Welling, there is no role of HIT. Yeah, we're just transferring the message. While a common way is to say that UT is the message that comes plus the current representation. Super simple. What is that? It's a residual connection. It's a skip connection. You have seen that, Sasa, right? In resonance residual networks. Yeah. So it's exactly the same way. I pass 3 skip connections. No matter what the update is, still I add the input. And so on, but okay. I'll skip other variants that maybe some of them had something interesting to say. Okay, so far in most of the cases we have been talking about so far node level predictions. We had updated representation of nodes and we're applying a classification head. Now in the case of edges, you may deal with such a message as an edge feature, or you may have the edge you may deal with such messages as edge features, or it was often the case that in many of the methods you derive edge features from the node features directly. A very simple way is that you do a dot product. You do a cosine similarity between the two representations. Okay, this makes sense, but it's very limited. Okay, it's very limited to binary classification or to one-dimensional regression, because the dot product will give you one scalar, and that's what you can do with that. Or another common way is that the whole propagation happens in terms of node features, but at some stage we concatenate two node features and we pass them through a function, which is, in the general case, can be a multi-layer perceptron, which maps in the output space that is related to the edge prediction task. Let's predict categorical labels now for the edges. Now for graph level predictions, this goes similar to the convolutional neural networks. We have a global pooling operation at the end. Let's take the representation of all the nodes of the graph and pull them together. You can see this as simple average pooling. Or you can see that while you pull, you also have some specific transformations of the node features, and so on, before or after the aggregation. And of course, it may also involve skip connections, that you're not only operating on the very last layer, but you're using internal. Now, a variant of that was proposed is to perform hierarchical pooling, because we have large graphs, and there may be structures that tend to repeat themselves pretty much, and dominate when you do simple average pooling all over the nodes. So some kind of hierarchical pooling was dealing with, I cluster the features in a way that is still differentiable, so it's some kind of soft assignment. I cluster, and I pull over a cluster, so on, until I reach to a holistic graph level representation. So now going to Sasa's question about, okay, what was that? That was not such a deep network. It was just like two layers plugged in together. How come? Okay, how come it is that in some tasks this had enough discriminative power? On the other hand, there are problems in training deeper networks when it comes to graph neural networks, and this has to do with oversmoothing. That when you add, because there is this propagation, and when you add many graph convolutional layers, then the many node features tend to become indistinguishable. You oversmooth. Some simple tricks now that having used in practice is that each processing block should be more powerful, right? So instead of having a simple linear transformations here, you have MLP, or you add also in your sequence of processing blocks, you add also processing blocks like MLP that do point-wise operations.
Are you speaking in this context of generalized message passing still about this transductive learning?
It doesn't matter. It holds for all the cases. So residual connections are another way, similar to ResNets, you know, that residual connections allowed them to train deeper networks because of the vanishing gradient, but here it's also because of the over-smoothing. Now, another solution was that there was a paper actually that figured out that maybe we can generalize the aggregation. Instead of handcrafting it to be average pooling or max pooling, we have a generalized mean. And this generalized mean here has a component-wise power p, then sums, and then raises again to component-wise power 1 over p. It's very easy to see that if p equals 1, then this is equivalent to average pooling. And one can show that the larger the value of p, this goes close to max pooling. Yeah, in the limit, it becomes equivalent to max pooling.
Yeah, we have seen it, right? In the, when we discussed the regularization, we had different P norms, and here it's now used as a pooling operation.
Yeah, as a pooling operation. Now in practice, empirically, the authors of this observed that, you know, you let the P free to learn, and actually this allowed them to train with deeper networks.
And the difference here is that there is no absolute power if I compare it to the P norm.
Absolute value? Yeah.
So that is signed.
That's true. Actually, this... yeah, no, it wouldn't work like that if you have negative values. This works with positive vectors, with positive vectors, which you had, you know, remember we had ReLU at the end of the processing block. Yeah, yeah.
Like the problem of making the features indistinguishable, I understand it, but would if our task is like whole graph classification, does do deeper networks work, or is there like does the feature distillation from the different nodes not work?
I think the understanding is that even if it's graph level prediction, still making everything distinguishable would not be helpful, because, you know, you're aggregating different parts, kind of more localized representations of the graph structure. So still it would harm it, even in those tasks. Okay, I'll try a bit fast to say that here in this work, Zhu et al. Says, okay, but actually this over-smoothing doesn't happen for all kinds of graphs, or doesn't happen for all nodes of a specific graph. Because here you see that I start from this node, I do 4 hops, and I reach pretty much the whole graph. But if I start from this node and do 4 hops, I reach a much smaller. 5 hops, still I didn't reach the whole graph. So, you know, does it make sense to have like a very, you know, rigid way of, you know, this neighborhood, or maybe we can somehow adjust it? Now, an internal intermediate result that seems useful in what they do is that they estimate the neighbor influence. Okay, how much the representation of a node after many layers is influenced by the original representation of another node. Okay? So they have a way to estimate that through sum of values in the Jacobian matrix between, you know, the representation of the two nodes. And then the useful thing is that they relate and they see that, oh, that's actually equivalent to the random walk distribution. So the random walk means that we start from a specific node, and then we make node transitions according to the affinity matrix. Okay, here we need a stochastic matrix, so we have the normalization that I talked about before. And you do hops like that, and then you see the probability of ending in another node. And actually they say that, oh, this influence as they measured it actually agrees pretty well with the random walk distribution, okay, which is pretty well understood and established. And this is useful in the following bit, that they say, to handle this over-smoothing, now I will take the representation. So this is the representation of a node. Okay, now we focus on a node. And this gets updated. Okay, layer 1, layer 2, and they get the representation of all the different nodes, and they combine them. Okay. Oh, of all the different layers. I said of all the different layers. And they combine them, to get the final representation. Max pooling over the different representations is a simple way to see it, and they do it. They concatenate and pass through a MLP, and so on. And even though this seems a bit, arbitrary and maybe hacky, so what is behind is that they say that actually the neighbor influence, the way that they were estimating it before, now becomes equivalent to the mixture of the many different random walks of the different steps, 0 step, 1 step, until k steps. And interestingly, they show that the mixture coefficients, of such a mixture, actually depend on the representation values of the output. So the most intuitive thing is that when you do max pooling over d dimensions, at each dimension you picked one of these k values. And if you count how many you picked each one, then this gives you the coefficient for the mixture of the random walk. Okay, so that was another way that allowed to go and train deeper networks together with previous things mentioned. Okay, so we have less 5 minutes left. I'm not supposed to touch my laptop, I think. Much. Okay, maybe I'll just go and talk a bit about the going back to some specific applications. So there is a small part that we're skipping that has to do with how expressive and what are the things that such graph neural networks can do. So earlier I mentioned, applications like with molecular graphs, so maybe now it's worth revisiting a bit to see how such things that were presented apply there. So you have benchmarks that correspond to some real-world applications, and you have a molecular graph, you have the nodes that are the atoms, and you have the bonds that are, you have edges that are the bonds between the atoms. And the task here has to do with graph level predictions. So you make a prediction for the whole molecular graph, and you have several real valued molecular properties. So it's a regression task. And here you have the different atoms, which means that you can associate a representation that you learn for a specific atom. And then at the same time, you have the bonds between atoms that carry rich chemical information. So these are extra features of the edges that one needs to take into account and as edge features. Okay. So all this taken into account so that you can end up with a graph level prediction. A bit of a similar case with protein-to-protein interaction networks, that you have proteins being the nodes and they're interacting with each other, and here the goal is to make node level predictions and to predict some protein properties. And maybe a bit of a different case. Here we're going back to the cases that the graph structure is not indicated by the data, right? But we create the graph based on adjacency, based on nearest neighbor information in some feature space. So this is the case with 3D point clouds and computer vision applications, where the mere input is a set of 3D points. Okay? We construct affinity based on that, and we have tasks where we make node level predictions, and it's classification task, which means that we're doing actually part segmentation of some objects, or here we have a whole 3D scene and we're supposed to do semantic segmentation given not the image here that we see, but a point cloud, and tell whether this point here corresponds to a chair or a table. So the input features here are simple 3D coordinates of a point. So starting by simple 3D coordinates of of a point and establishing relationships through the affinity matrix, one can have such a result. Yeah? So here it is an inductive setup. We train on different scenes, different graphs, and then we're supposed to apply this on a new graph. That's all from me for now. Any final questions? Yeah.
So you speak about this permutation invariances or equivariances. And if you have a network like which is partitioning, so there are
Can you say again? Quite?
the network is like bipartite graph,
Mm-hmm.
users and products. Why would we want like for permutation invariance in that case? Are there some specialized graph neural networks which are okay?
But
Different kind of graph components working on them?
But wouldn't you wait? In this case, permutation invariance, it means I swap the order of two users. I swap the order of two users, and but the users carry then interactions with them, right?
Can you swap users and movies?
That's what we mean, because when we're saying about the permutation, you permute not only the nodes but also the interactions. So as a user, it's about like the ordering of listing the nodes in the representation matrix or in the affinity matrix. First row corresponds to that guy. Second row corresponds to that guy.
Yes.
Yeah. So
The question is, if you know the graph is like bipartite and then you don't want to permute users and products, then maybe you could have a more extended, like a richer class of transformations used. Maybe try to combine information from the users and from the products.
no, but the permutation is about.
Well, you introduce like a flat graph and then
What?
only nodes on the graph.
Yeah. 1, 2, 3, 4, and then you have the same, but somehow the way you're listing, you're ordering the nodes in the representation, so this becomes 4 and this becomes 1. The permutation invariance should still hold in that case. It's the same graph. It's again the same graph, no matter, despite the fact that we swapped the ordering, which means that the ordering means now that when I have the features and the affinity, they're not the same. The entries are permuted there, so it still holds unless you mean something different that I. Yeah. Yeah. Mm.
But it also like the network structure doesn't necessarily have to be equivalent or invariant with respect to permutations of the users and nodes. It would allow like for a larger class of operations.
I'm not sure.
No?
Okay. Thanks everyone. Yeah. Okay. Some slides are a bit incomplete. I can add the reference at the bottom of the slides before they get uploaded, right? So, no. That's not what you mean. Technically. Right. Some people have manually annotated. Yeah, that's what you mean. Yeah. But somehow, because now we're laughing because indeed it is very costly. Yeah, maybe you can also go in semi-supervised, that I don't annotate all the points, but I just click here and there, so that becomes much faster. And then a graph neural network can help with that. You mean transformer networks? Yeah. But yeah, but transformer networks already have some also like no. I'm not an expert in how the different datasets are created, but indeed some datasets are created like that. You have correspondence between, you know, like RGB data and 3D point clouds, and if you annotate one, you transfer between one and the other. Yeah. So for sure, I wouldn't expect that they would be clicking on points in the 3D point cloud. Semi. Yeah. True. Yeah. Other stuffs now that there are networks that can do, you know, give you good segments in an image. You start with that, and then you assign one label per segment, and then you fix whatever maybe this network got wrong. There is the segment anything model that is pretty good in that. Yeah.
Related to what colleague asked, so we've derived that we can do like real-level motivated graph inference and graph processing, which is like sequence invariant, right? That's the whole point you've been discussing.
Yeah.
You can have an arbitrary data, and as long as you have the relationships,
Yeah.
then it works somehow. Well, if you have a transformer with an all-to-all attention, that's also like a general sequence processing.
Yes.
Network.
Good.
It's not structured with the permutation.
Good.
Invariance.
And that's why, wait for it, that's why also these lectures come, you know, one after the other, because there is direct relation, but like a much higher flexibility of what transformers do. And then we have encodings of, you know, what is the order in the sequence. So something will change there. Yeah. Yeah.
Just now, can you share maybe, have there been any comparisons, like direct one-to-one on the same task? Let's say like the point cloud labeling. Has anyone, you know, tried to compare a GNN
Uh,
with an all-to-all transformer?
it's very good question. I will try until next week to figure out what is a good bulletproof, you know, comparison, because sometimes I was saying before, in some tasks you really need to inject a fixed structure and a fixed affinity, because in transformers you let this totally free, and it might learn things that do not help you for your so each one has their own advantages.
It seems that there is message passing graph neural network that we introduced, they are more general than
Yes, actually, there is also, I chose not to talk about it because there is what's called attention graph networks, maybe, that are inspired by attention processing and transformers, and actually they bring the two things, you know, very close, and they fit in this message passing framework. But we're going to talk about it next week better, and maybe we can make the relation when we talk about transformers. Yeah.